Great. So the final talk in this session is going to be given by Jun Bi. Jun Bi is a professor in the university at Tsinghua, and he's going to be talking about his experiences deploying SDN in an operational setting and extensions to OpenFlow and SDN to accommodate the challenges he learned there.
Okay, good afternoon. I'm from Tsinghua University. And as you may know, Tsinghua University also operates the China Education and Research Network. So I'm presenting on behalf of both of them. Okay, basically my talk will cover two parts. The first one, I will introduce our existing work to have IPv6 source address validation by using OpenFlow. So I have the same feeling with most speakers today. With OpenFlow, it's very easy for us to introduce a new service to the network. Running one single application is easy, especially in a limited scope. In the next step, we are thinking to build infrastructure to support arbitrary new service and new architectures. So taking that as a role, especially having SDN as a fundamental to support that, I think there are still some design challenges. So I'm going to present some of my personal viewpoints. For example, you can see in the forwarding abstractions, do we need to support the non-IP or so-called post-IP architecture? Right now we know OpenFlow is successfully to support IP architecture forwarding abstractions. How about the non-IP structure? And also for the control abstractions, how to design scalable network operating system and a programmable, manageable virtualization platform. For this item, I think speakers before me, they addressed this topic. That's really a great research and design topic. And if we really want to run that in large scale, then multiple operators will be involved. One operator cannot control the resource owned by another operator. So here we need a negation abstraction. So right now we are talking about control abstractions. Then how we design the negation abstractions between the interdomain scenario. So that's basically what I'm going to talk. Our new service is source address validation. So first, I will let you know the source address spoofing is still a problem. You can read those documents or discussions. Right now, we have a great technology, URPF. However, it will cause the false positive in some situations because it only generates filtering table based on local information without the global knowledge. So in this case, we propose a new method named CPF. It calculates the forwarding, the fielding tables based on global knowledge. In the first version of CPF, we make use of existing protocols between our software and the network devices. You can see we are using SMP or some packet sampling protocols. As it's Xflow, it means the NetFlow or SFlow. And also we use Telnet as the control method. For this version of CPF, we already implemented and deployed in that 100 IPv6 campus network. And in the new version, we are using OpenFlow. I will let you know why we migrate to OpenFlow later. Here is a brief introduction to CPF. You can see we install a management system in the left side in the campus network. It will talk with those routers in the campus network to get the IPv6 routing tables by SNMP protocol. Then the management system will calculate the forwarding tables and download the tables by Telnet to the routers. And the system can also generate the spoofing alarms. So the management software will also get sampled packets by Xflow, NetFlow, or SFlow. and it will match the flow information table. If there's a mismatch, it will generate alarm. As I mentioned, we deployed in 100 university campus networks, and we met some problems. I will list those challenges in the next page, but here basically we have two problems. One is there's no standard interface between our control software and the network devices. So it's really painful when we deploy it. When we deploy in a new university, if there's a new brand name equipment, we have to change our have a software revision of our management system. It's really painful. The second is there's no direct full control to the routers in today's IP architecture. So it will bring some problem like false positive. I will explain in the next page. Here you can see the interface between our management system and the router is not standardized. For example, the IPv6 routing table, a different router company, or switch company, they implement a different version of MIPS. So we have to enhance our software to handle all the situations. It's really painful. And also you can see for packet sampling, it's not standardized yet. And there's no full control. We have to use Telnet to download that access list to the router. And it's good for very simple configuration. If the configuration is complex, then it's very dangerous to install the ACL by scripts. So in most cases, we have to install the ACLs manually. And also, you can see the last challenge is the most critical one because the state in our management system and the state in the network, there's the convergence time is there's a longer convergence time, so it may cause slight false positive when we do filtering. That's a critical problem. With OpenFlow, we can resolve those problems. OpenFlow provides the standard interface between our control software and the network device, and we can enhance the OpenFlow with small extension to support like packet sampling so that we can fully control that network device. So that's the reason why we choose OpenFlow. We have architecture consideration like the central control scheme, and it's flexible for those innovative but long-tail applications, especially for universities for our new research result. And it provides standard interfaces, and we found the implementation is easy. In our work, we upgrade legacy routers by inserting a shim layer software in that router, then it can support OpenFlow easily. We call it Open Router. And for any function, it's not supported. It's not supported by the standard OpenFlow interface yet. We can do a small extension to support that. So we can full control the network equipment. So this is the architecture of current router architecture. We just insert a shim layer so that it can support OpenFlow at the legacy routers. And they will also have a small extension like packet sampling or the report of layer 3 IPv6 routing table changes so that we can enhance the performance of our source address validation and filtering performance. And we implement that with some domestic vendors. And you can see we already built a testbed in Tsinghua campus networks. And based on this testbed, we run CPS as an application. And so far, we get very good result. I think it's a great technology to introduce those new IP services. Especially, we reduce those filtering false positive because we can get the latest network status quickly than before. Then we are thinking how we can do more things like this. As I mentioned, we operate Sirnet, and we have a second version of Sirnet called Sirnet 2. It has 100 campus networks and 25 autonomous systems. So in the next step, we are going to deploy that in a larger scale. And since we have multiple autonomous systems, we also need to deploy inter-AI software address validation. Then we need to think about how we can install application in the interdomain scenario. And once we have this platform, we are thinking if we can use that for other research topics, like we are doing research on content-centric network. That's a totally new architecture than IP. If we can run that on this platform, it's good. So we are thinking to have that platform to arbitrate new service and new architectures. So right now in China, there's a project being planned. You can see we name it FINE. It's a Future Internet Innovation Environment. We hope SDN can be the fundamental of that platform. So considering that as a role, let's review the SDN architecture and to see what what more work needs to be done. If you run it in a large scale, as I mentioned earlier, you need to consider interdomain case. Then maybe we need abstraction for programmable negotiation between operators. Right now, I think SDN is good at the first part, the intra-domain, by designing abstractions for programmable control inside the domain. We may need to consider standard interdomain policy negotiation abstraction. And this picture shows the intra-domain case. You can see the bottom, the yellow box is the forwarding abstraction, and OpenFlow certainly is a good example on IP architecture. And if we support other architecture, I will take NDN or CCN as an example in the next slides, how we need to enhance that. And this forwarding abstraction provide APIs of local view. Then on top of that, the network operating system will translate that local view into a global view and provide the APIs. So the application can run on top networking operating system directly, like today's OpenFlow application. Or if you write in a very large scale, like millions of applications, millions of nodes, we need a virtualization platform with a management system and designing tools. I think speakers before me, they are addressing this topic. Next, I will talk about the forwarding abstraction for non-IP or post-IP architecture. For those audience who are not familiar with content-centric network architecture, we'll have a very brief introduction. So here you can see they changed the narrowest. It's not IP anymore. It's the content layer. And the NDN router won't look up IP address. They will look up names. And here is that procedure. They have a new component called content store, and two types of packets. One is interest packet. That's actually a request for content. If it matches the content store, the user will get the data. That's the benefit of this content-centric networking. And they have a new data structure called pending interest table, PIT. So if the content is not in the content store, the router will look up the PIT table. If somebody else asked the same content, then the interest packet won't be forwarded because somebody already asked it. Otherwise, it will look up the forwarding table and forward the interest packet. When the data come back, it will check the pending interest table. If somebody asked that content before, it will deliver to that interface. Otherwise, it will be dropped. And certainly here, there is the catching update policy to store that data in content store. So that's basically how NDN working. So we take that as example. If we implement that in OpenFlow, so it may like this. We have NDN controller on top of the network operating system, and we have those tables as flow tables, multiple flow tables in the open devices. Here we have flow table 0, the content store, flow table 1, the pending interest table, and flow table 2 is the FIP table. Looks good. However, I still have some discussions. One is how we can add a new forwarding component. As I mentioned, there's a new forwarding component named content store. There are multiple ways we can position this new component. One is we add that catch inside the open devices. The second is we can have our bypass devices, but co-located with the OpenFlow devices. And the third choice is, since we already have our network operating system and the virtualization platform, maybe we store the content in the cloud. And those different store position will lead to different forwarding abilities. So here I list, if you have these different choice, what forwarding abstractions you need to add. Maybe in this architecture need more atomic, like you need to, the device need to generate a packet without the control of the controller. They need to run a catch update policy by itself. So in this case, not every action is controlled by the controller. And another discussion is how we can add new forwarding actions. I won't go to the detail. You can see for those red characters, red sentence, they are new actions the current OpenFlow standards doesn't cover. So we need to add those new actions. So if we know what the architecture is, we can still design it. But the question is how we can extract forwarding abstractions for arbitrary new architectures which coexisting in the same platform. I think that's the design challenge. So my personal viewpoint may be naive. I think maybe in the future we may permit multiple forwarding abstracts to run in a hybrid mode. Like we can have OpenFlow as standard for some set of architecture, but maybe like the service ID Jennifer mentioned in the beginning as the second choices. But all of them support the common same network operating system so that our application designer can still use the same interface, can still do the programming network. And second is the network operating system. I think many people in this community are working on that. I just want to add one comment. We may need to consider also run NOS inside the router for some consideration like performance or robustness. Here, even though we run NOS inside the device, it's still a separation of control and forwarding because you can see there's still clear boundary between the forwarding abstractions and the control abstractions. And also need to handle the conflict if you run millions of thousands of applications. I think speakers already addressed that problem. And for virtualization platform, basically that's a mapping from the resource request by the application logical requirement to the physical requirement. And I think some design tool is really needed, as well as the management tool, and the speaker before me addressed this problem. The last one is interdomain case. So you can see in the future we may have different applications sitting on top of SDN. Today, when we have an interdomain communicating requirement, we design a specific protocol, like for IP, we designed the BGP. And for the inter-AS source address validation, we designed our own protocol. We name it SMA. And I believe those new architecture, like in the end, they're going to design a new interdomain protocol by themselves. I think that's not good. If we have an interdomain abstraction, then those application designer, they can make use of that interface. Then things will be much simpler, before, in the future. So here I give an example. This may be not a very ideal design, but it's the examples. Here we use XML template as the policy negotiation abstraction. So when packet pass the boundary between different domain, the negotiated policy will apply. Like in IP network, the packet will be processed based on the forwarding path. And in our interdomain source address validation, the packet will be processed by signature checking. So we need the abstraction can handle those cases. So here we have 3 fields. One is mandatory field, the basic information of your application, and at least the reachability information in type length value format, and the optional field with some known requirement, but not to be supported by every autonomous systems. And also user-defined, they can define their specific requirement for inter-domain policy negotiation. Okay, finally, in this talk, I introduced our existing work on the IPv6 source address validation using OpenFlow, and have some discussion if we run SDN in the large-scale network, especially to support arbitrary new service and new architectures, some challenges. Okay, we hope SDN can be the fundamental of our future internet innovation network. Thank you very much.